So title for my talk is Electromechanical Device with a Transmon Qubit, which is a fairly technical title, and I'll try my best to simplify it to engage a broader audience. So before I begin, I would like to acknowledge the funding agencies who gives us money, and equally the research group, the research team that I have at ISC who does all the hard work. I get to give the talks, but actually they are the real heroes who are doing work behind the scene. So title of my talk is Electromechanical Device with a Transmon Qubit. So what I'll try to do is give a flavor of what this device is and break it up into components and try to tell the importance of such devices. And towards the end, I'll show measurements and summary and outlook of this work. So there are two components in this device. One is a transmon qubit and second is electromechanical. So let me begin with the transmon qubit first. Okay. So a general introduction to circuit QED and superconducting qubits. So circuit QED is an analog of cavity QED where atom interacts with the electromagnetic field. In circuit QED, the role of electromagnetic cavity is replaced by these LC oscillators formed by capacitor and inductors. And role of atom is taken up by the superconducting qubits, which are essentially nonlinear oscillators formed by the inductance of a Josephson junction. Okay, the free energy of a Josephson junction is given by this relation. So unlike in a linear oscillator, we have a quadratic dependence on the node flux. Here, the energy depends as a function of it's given by cosine phi, and EJ is the Josephson energy of this junction. This slight change in the potential energy landscape modifies the energy eigenstates completely. For a linear oscillator, we have energy eigenstates which are equally spaced in energy. But if you modify this potential term to cosine phi, we have energy eigenstates which are not equally spaced. Okay. What happens due to that? That if you cool down such an electrical circuit to very low temperature, something like 10 millikelvin, and make the oscillator frequency of the order of few gigahertz, just because of high frequency and low temperature, the system most of the time initialize in the lowest energy eigenstate, which we will label as ground state. And if you try to bring any microwave signal to make an excitation from the ground state to the first excited state, you can basically think of the dynamics of this circuit within the subspace of these two levels. So you can forget about any other transitions because they will be off resonant with any external drive. So these nonlinear oscillators at low temperature and with sufficient high frequency, we can treat it as effective two-level system. So we can label these eigenstates as G and the first excited state as E and treat this oscillator, nonlinear oscillator, as a superconducting qubit. So this has been the basis of Professor Kavita earlier introduced that, once you have these two-level systems, you can use them, you can have them coupled to each other and use them for quantum computing. That's one way. And one of the way of doing that is to have these superconducting qubits coupled to a cavity so that a readout on these qubits can be performed. Okay, and typically you put them together with some capacitances to get some transverse coupling between the readout cavity and the superconducting qubit. For the purpose of this talk, I will not be focusing on the quantum computing aspect of these superconducting qubits. So this particular one is an example of a transmon qubit, which has been the working horse for quantum computing. I will be focusing on slightly different aspect of these superconducting devices, which I suppose will be clearer very soon. So the second component in my talk is nanomechanical resonators. These can be think of as nano structures or nano or micron scale structures which are suspended and clamped from two sides. So these are like a micron version of guitar strings. Okay, since the speed of sound is much smaller than the speed of light, typically if you try to plug these oscillators, they have resonant frequency in the range of 1 megahertz to 100 megahertz. And because their frequencies are not in gigahertz, so even if you cool down these resonators to very low temperature like 10 millikelvin, there's still some thermal fluctuation left. So typical thermal fluctuations in these structures at 10 millikelvin temperatures are order 10 to the power minus 13 meter per square root hertz, which is an order of magnitude larger than the quantum 0-point motion. If you try to work out how many phonons would be there in a fundamental mode, one can apply simple equipartition theorem, and you would see that they are order 50 to 500 nanometer. So the question that we ask in our lab is, can the circuit QED platform be used to control the quantum state of a massive oscillator? And what I mean by that, if we can we devise ways by integrating qubit and these mechanical structures together so that any arbitrary quantum state of motion can be prepared in the mechanical oscillator? So that's the question we address. So apart from, obviously it's quite important from a fundamental point of view, but, such devices also have applications in quantum communication. So for example, like I said, speed of sound is much smaller. So you can have information stored in these mechanical vibrations for much longer time. So if you're thinking of creating delay lines, you can have Gaussian or non-Gaussian states stored in the vibrational mode, and then later they can be retrieved. So these are some of the aspects why these devices are important. Okay. So one way to have mechanical structures coupled to electromagnetic mode is to make capacitor. Right. So this is here is one such example. What you see here, this circular disc is a micromechanical resonator. And this is a drum-shaped mechanical resonator, which is patterned on a silicon substrate. So it's a capacitor where the top plate is mechanically compliant, so it is free to vibrate. It is shunted with an inductor, which is in this meander form, and the value of L and C, inductor and capacitors, are chosen such a way that the circuit operates in few gigahertz frequency range. Okay, so the resonant frequency of this circuit is given by simply 1 over square root LC, but now we have a situation where capacitance depends on the position of the top plate. Okay, so if this top plate vibrates, we will have a modulation of the resonant frequency of this electrical circuit. So if you work it out, it turns out that, the figure of merit here, how strong the coupling between the microwave cavity and this micromechanical resonator is, that's given by this quantity G naught, which is defined as the shift in the cavity frequency due to the 0-point motion of the mechanical resonator. And the type of coupling is very much like radiation pressure coupling, where intensity of the beam is coupling to displacement. Okay. Now, if you think about it, this setup is essentially using the charge degree of freedom to couple mechanical resonator to the electromagnetic mode. Okay. So the question that we asked in our lab was that, if we write down the Hamiltonian for such an electrical circuit, we have charge degree of freedom and we have flux degree of freedom. Would it be possible to devise a similar device? Would it be possible to design a similar device where we could use we could use the flux degree of freedom? Okay. So the question then it boils down to that: can we make inductor which is displacement dependent, and would it be possible to integrate a circuit QED platform when we design such a device? Okay. So these were the questions, and if you think about it, that if you take any wire, for example, and try to deform it, the change in its inductance value will be very small just by changing the geometry of the wire. So what we come up with was a very different idea than deforming the geometry, but it comes from DC squid. Okay, so imagine two Josephson junctions in a loop. It turns out that due to the interference of superconducting phase across these tunnel junctions, this element would act like a nonlinear inductor. Okay, so this inductor of such an electrical component is given by some critical current of these junctions and absolute function of cosine pi phi by phi naught, where phi naught is the magnetic flux quantum. So inductance of such a loop, as you can see from this formula, depends on the applied flux. So this squid loop acts like a nonlinear inductor, okay, and its inductance value depends on the magnetic flux, which is threading the loop, okay, and it is also a periodic function, and every half flux quanta it repeats itself, okay. So now we have an inductor by putting this in a squid loop, which has periodic inductance, magnetic flux dependence inductance, which makes it nonlinear. Okay, and this is the one which we want to use to realize the qubit mode. So if we go further and release one of the arm of the squid loop and make it suspended, now you can see that displacement of this wire would cause a change in the magnetic flux and hence change in the inductance value. So by making one of the arm of this squid loop suspended, we can realize a displacement-dependent inductor. Okay, so this is the idea that we pursued to realize a circuit QED device. So the next question we wanted to ask ourselves that, can we choose these inductance value in such a way that we can design a transmon qubit with such an inductor? Okay, and the answer is of course yes. That's why I'm giving this talk. So what you do is you take this displacement-dependent inductor and shunt it with a capacitance. And again, a lot of simulation work goes here in designing the frequency correctly and retaining the sufficient enharmonicity so that this oscillator can be referred as a transmon qubit. Okay. For readout purpose, what we do, we couple it to a 3D waveguide cavity, which is just a linear oscillator, and then a microwave signal can be sent to this readout cavity, which will have this quantum state of this nonlinear oscillator imprinted on it. Okay. If you quantize these two circuits, you would see that this is a linear oscillator, so the energy eigenstates are equally spaced. But because this is a nonlinear oscillator, the energy eigenstates are unequally spaced, and we are working in the subspace of the first two eigenstates. Okay. On top of it, we have a mechanical mode here in this nonlinear inductors. So each of these eigenstates are labeled by G and E. They contains many vibrational levels. Okay. Since mechanical frequencies are much smaller than the eigenvalues for G and E, so they will be very closely spaced to each other. Okay. So this is the schematic of the device. How do we realize this in the lab? So what you see here is the fabricated device that we made in our lab. This central line here, over which I have placed my laser pointer, that's the capacitor. Okay, this is a single. This is the capacitor which is coming here. The central part of this figure contains the mechanical resonator in the squid loop. I will show a zoom in shortly. And there are some other electrodes which are used to kind of have the external connection made to the mechanical resonator and the qubit. Okay, this entire chip goes inside a 3D waveguide cavity, and which has an input and output port to measure transmission and hence record the qubit state. Okay. We have also added a port to drive the mechanical resonator if needed. All right, so this is the SEM image of a device. What you see here is the zoom in of the squid area. These two tiny islands here, these are the Josephson junctions, and it completes a loop here, and this is the electrode which goes and becomes grounded. The top part here is the capacitor, which is shunting this nonlinear inductance to realize the qubit mode. The T-shaped like structure that you see, that's the electrode which has been added to actuate the mechanical resonator at will if needed. Okay. So typical length scale here are the length of this mechanical resonator is 45 micron, and it has a thickness of about 100 nanometer and has a width of something like 300 nanometer. Okay. So this beam can have two vibrational modes. It can vibrate in plane and it can vibrate out of plane. Okay, so if we apply magnetic field which is perpendicular to the plane of the squid loop, we will be sensitive to the motion of in-plane vibrational mode. Okay, if we apply magnetic field in the direction in the same plane as the squid loop, we will be sensitive to the out of plane motion of the vibrational mode. Okay. So for this experiment, what we do is put this fabricated chip inside a 3D cavity, which is nothing but just a metallic box, rectangular metallic box, and the dimensions have been chosen such that it has a resonant frequency near 6 gigahertz. On this metallic box, we also add a bunch of microwave connectors so that we can send in microwave and see what comes out. Okay, so this is the structure of the device. The entire thing then gets inside a dilution refrigerator, cooled down to 10 millikelvin. We have placed a very small magnet here, superconducting magnet, to flux bias the squid loop. Okay, and these are the microwave cables with lots of filters, which brings and takes in the signal. All right. So just to summarize what kind of device we are looking at, we have a flux tunable qubit mode, which is designed to be transmon of frequency something like 8 gigahertz. It is coupled to a cavity mode which is designed at 6 gigahertz through this dipolar coupling. And since the frequency of the qubit is modulated by a mechanical mode, there is also a longitudinal coupling between this qubit and the mechanical mode. In addition, we have access to both the photon drive and phonon drive at will. Okay, so this is very similar to what we have in trapped ion system. So for example, if you think from a qubit point of view, what we have here is a two-level system which has got a motional degree of freedom, which is similar to trapped ion. Okay, and if you think it from oscillator point of view, we have a mechanical resonator which has an internal degree of freedom of spin half. Okay, so now this internal degree of spin half can be used to create some non-classical states of motion. Okay, so that's the long-term idea that we have. So first, when we have such device cool down, we start characterizing different parameters. So first we measure the transmission through the cavity, which is called a singleton spectroscopy, as the magnetic flux through the squid loop is varied. Okay, so what we see here is the standard vacuum Rabi splitting. So qubit mode initialized somewhere here at 8 gigahertz, somewhere far above. And then as magnetic flux is increased, it tends to come down because inductance value is changing, and then becomes resonant with the cavity somewhere close to 0.33. Okay, so this color plot here is showing the transmission. Red means high and blue means low. So these lines are really showing the frequencies at which the transmission is max, and hence the resonant frequencies. Okay, so we at around phi equals to 0.33 phi naught, we have avoided crossing, which is showing the hybridization between qubit and the cavity state. And as we continue to increase the magnetic flux, the qubit goes to a minimum frequency at 0.5. Like I said, it has a periodicity of half flux quanta, and then again start to go up, and we have avoided crossing again. And this pattern will continue as if we increase the magnetic field flux further and further. So such measurements are useful because they let you characterize the qubit mode, cavity mode, and the coupling rates immediately. So from this measurement, we determine that qubit mode has come out where we designed it to be, around 8 gigahertz. Bare cavity frequency is near 6, and the qubit cavity coupling is ordered 85 megahertz. Okay, and like I said, if we are applying the magnetic field, which is perpendicular to the plane of the squid loop, we will be sensitive to the in-plane mode of vibration. Okay. So next question comes, how do we detect the vibrational mode from such measurements? Okay, so like I said, you can continue increasing the magnetic flux, and this pattern will repeat itself. Okay, so this first, the figure on the left-hand side, that shows the spectroscopy of the cavity in the first lobe of magnetic flux, but we can go to higher lobes, something like 195, 196, 197, and this pattern continues to repeat itself. What is the advantage of using the higher lobes is that, if you bias, for example, the magnetic flux somewhere close to these slopes, where the change in frequency is highest, then mechanical motion comes out as the phase fluctuation of the signal that comes out from the cavity. And the coupling between mechanical motion and qubit mode is also largest when you operate at higher magnetic value of flux. Okay, and that's easy to understand that, given a large amount of magnetic field, a small change in the displacement will result into larger change in flux. So the coupling between mechanical motion and the cavity or qubit would be largest when we apply large magnetic field or large magnetic flux. Okay, so that's the idea, and mathematically also one can see it. That coupling between electromechanical coupling between mechanical mode and the qubit scales as the number of the flux quanta that are passing through the loop. Okay. So what we do next is we bias the device and send in a microwave at this frequency and bias it close to this fast slope and look out the phase noise of the transmitted microwave. So what you see here is a histogram of such measurements. We are plotting the power spectral density of the microwave signal that comes out from the cavity. And I would like to remind here that the strength of the microwave signal that we send in is actually very small. It's something like 0.1 photons on an average. Okay. So this is the average plot. We measure a mechanical frequency of something like 6.5 megahertz, and it has a line width of something like 6 gigahertz, which corresponds to a quality factor of 10 to the power 6. So, the mechanical quality factor here is order a million. Okay. So after establishing this mechanical mode, we want to characterize our coupling. So the advantage of measuring the thermal noise is that it allows you to calibrate the electromechanical coupling directly without any fit parameters. So here is what we have measured is the electromechanical coupling as the magnetic flux through the squid loop is increased. Okay, the maximum coupling that we have measured is close to 4 kilohertz, And it's actually quite large as compared to usual capacitive coupling schemes. So the usual capacitive coupling schemes, like I showed you earlier, they have a fundamental limitation that coupling cannot be pushed above 200 hertz or so. But here, by the virtue of that we can apply more magnetic field, the coupling can be increased. We could take the coupling up to 4 kilohertz. And the maximum coupling that we achieved in our experiment is limited by the maximum field that we can apply in our magnet. If we had a bigger magnet, then you can see that this coupling can be increased further up. Okay. So what is the consequence of this large coupling between qubit and the mechanical resonator? Okay. So one of the consequences that we looked at is how the qubit spectrum is modified due to this large coupling. Okay. So the experiment that I just discussed with you is done near the resonant limit. But you can imagine that we can increase the flux further and further and place the qubit somewhere at a higher slope so that coupling gets further high. So by detuning the qubit like a gigahertz away from the cavity, we could push the qubit mechanical coupling to 40 kilohertz. But now because qubit and cavity are far away in frequency, it's very hard to do the readout of qubit state through one-tone spectroscopy that I showed earlier. So in order to measure qubit spectrum, we resort to two-tone qubit spectroscopy. Okay, so this is again slightly technical aspect of it, but we park the cavity somewhere at 6 gigahertz and detune qubit near 5 gigahertz. And what we do is we send a spectroscopy tone near the qubit transition while maintaining a probe tone at cavity frequency. Okay, and moment we hit a transition, any transition in the qubit spectrum, we will see a change in transmission at the probe. Okay, so that's how the idea of two-tone spectroscopy worked. Okay, so we wanted to ask that due to this large electromechanical coupling, what is happening to qubit spectrum? Okay, so these are the measurements measurement results that we see in the qubit spectrum. So what we see is the usual qubit spectrum when the mechanical drive is off, and as we start to increase the mechanical drive strength, the qubit spectrum splits with two global minimas, and then there are a lot of interference patterns between the two valleys. Okay, and this seemed like a very simple model where qubit is being driven transverse and in longitudinal direction simultaneously. And it turns out that although it seemed like a very simple model, there is no analytical solution for it. So one has to resort to numerics in order to understand the qubit spectrum. Okay, so these are results from numerics of such a Hamiltonian, and they fairly matches well with the experimental data. The effect is known as Landau-Zener effect when you drive a two-level system simultaneously with along transverse and longitudinal direction. Okay, as its system undergoes through many various avoided crossing region, it accumulates a Stackelberg phase, which results into these interference fringes. Okay, in our experiment, these fringes are not very sharp because the T2 times was smaller than the time period of the mechanical oscillation. But if we can improve the T2 time of the measurement, then these fringes should become much sharper. Nonetheless, the theory captures them quite beautifully. Okay, so just to summarize the talk, what I showed that we have a new flux-based coupling to realize a hybrid device where we can integrate a qubit to a mechanical mode. We can achieve single photon coupling rates of order 40 kilohertz. As a consequence, we see the onset of Landau-Zener Stackelberg interference. The current experiment has a limitation that the device has line width of 12 megahertz and mechanical frequency is order 6 megahertz. This puts us in unresolved mechanical sideband limit, and we could not do sideband resolve techniques to cool the mechanical oscillator to ground state. So what we need to work on further is to reduce the qubit line width, and if we can reduce it smaller than the mechanical frequency, we can apply sideband cooling techniques to have the mechanical resonator operating in the quantum near the quantum ground state. Okay, so with that, so some of the details of this work are also available in this preprint. So with that, I would like to thank you for your kind attention, and thanks again, Academy, for giving this opportunity.